we have our suite of functions that we now have to use. Polynomials were the first things we learned to differentiate. Let's have a look at our exponential function. How do we handle that? And what we saw, you may recall last year, was that if we have something to the base e, our natural base, e to the function x, when it comes to an exponential, we actually differentiate the power. So you differentiate the power, that answer goes out the front, the power does not change. So it stays as e to the function x. That's when it's the natural base of e. If it's not the natural base, some other base, so a to the power of function x, we still do it exactly the same, but the difference is we also multiply by the natural log of the base. Now I've written it as log. More commonly I think people just write ln for the natural log. But remember, if you see log without the base written on it, we assume it's the natural base. The world's easiest calculus question that could ever be asked. Y equals e to the power of x. Differentiate y is e to the power of x. Well, we differentiate the power. The power is x. Differentiate x, you get 1. So the answer is e to the power of x. The world's easiest question. E to the 5x, differentiate the power, you get 5. So that goes out the front. 5e to the 5x. Remember, the power does not change. In this case, 4x plus 3, but again, we just differentiate the power. 4 goes out the front. Doesn't have to be a linear function, the power could be anything. X squared plus 3x plus 2, differentiate that. 2x plus 3 goes out the front. That's the idea. Woohoo! Product rule. So we now have a function in front of e to the 4x. That has to be dealt with as well. So our product rule, write down the first, diff the second, plus, write down the second, diff the first, write down the first. Well, the first function I'm seeing is 3x squared. Differentiate the second function. Well, the second function, e to the 4x, so that becomes 4e to the 4x. Plus, write down the second function, e to the 4x. Differentiate the first function. Differentiate 3x squared, we get 6x. Let's tidy that up. Now, of course, with the exponentials, because the power doesn't change, you're always going to get a common factor of the exponential there. So I've got e to the 4x, I can pull that out. This one also has other common factors. There's a common factor of 6 and a common factor of x as well. Do you have to do that? And I guess no, you don't. It all comes down to what are you using the derivative for. If I was to now go and find stationary points, well then it's easier if it's factorised, because we know stationary points occur when the derivative is 0. So you're solving something equal to 0, you would like it in factored form, because each piece could possibly be 0. Chain rule, anarchy. Bring down the power. All right, bring down the power, 7. Lower the power, 6. Diff the inside. So what's inside the parentheses? E to the 3x plus 2, differentiate that, I get 3e to the 3x. Let's just tidy that one up. 21e to the 3x, e to the 3x plus 2 to the power of 6. How could we forget our quotient rule? Square the bottom, write down the bottom, diff the top, minus, write down the top, diff the bottom. Square the bottom, that's the easy bit. Whack some parentheses around it and just put power of 2. Square the bottom. Write down the bottom. Well, the function that's on the bottom is e to the x plus 3. Diff the top. The world's easiest derivative. Differentiate e to the x, I get e to the x. Minus, write down the top. E to the x. Differentiate the bottom. There it is again. World's easiest derivative, e to the x is e to the x. Be very, very careful. Remember, when you're multiplying, you add the powers. So easy to multiply e to the x with e to the x and get e to the x squared by mistake, because you're thinking you're multiplying. Remember, add the powers. So we, of course, get e to the 2x, which in this case subtracts from the other e to the 2x, and I'm just left with 3e to the x on e to the x plus 3 squared. All right, let's do a question where we're using it. Finding the equation of the tangent. That was one of the first sort of calculus problems we looked at. So the tangent to the curve e to the 2x plus 1, which would be, if we were to visualise it, it's our exponential, a little bit steeper because of the 2x, isn't it? And it's shifted up 1. Okay. At the particular point 1, and the y value we've got as an exact value of e squared plus 1. Okay. Need my derivative in order to find the slope of the tangent, because remember, the first derivative is also sometimes called the gradient function. It's the function that allows you to find the gradient. In this case, it's 2e to the 2x. That's the formula to find the slope of the tangent. It's not the slope itself. We need to substitute in the required point. Our one is when x equals 1. So the slope of the tangent here is 2e squared. Point slope formula. Y minus the y value, which in this case is e squared plus 1, equals 2e squared times x minus 1. Look, it's not pretty, but it is a linear function. Because remember, e, of course, is just an irrational number. It is a number, but that's what we get. 2e squared x minus y minus e squared plus 1. And there it is in general form. Oh, here's one where the base is not e. That's all right, we do it exactly the same. Differentiate x squared, we get 2x, but remembering to also multiply by the natural log of the base. So the log of 4 is in there as well. Now notice I've used parentheses around the log 4. That's to avoid any ambiguity. Imagine if I did not put those parentheses there. It would be so easy to look at that and think you're saying the log of 44 to the power of x squared. If I'd put the log 4 at the front without parentheses, it would look like I'm saying log 42. If I put it at the end, it would just look funny. 2x, 4x squared. So I tend to do it that way. Put the parentheses, and there's no ambiguity at all. We know exactly what we're talking about. It's 2x times the log of 4 times 4 to the x squared. Uh-oh, hang on. Differentiate log, we haven't talked about that. But we can do it, because what I do is rewrite this. Remember, to undo the log, we do the inverse. The inverse of log is the exponential function. So and I don't know if this is a word, but I say it all the time, I exponentialize both sides. So the left-hand side becomes e to the power of y, the right-hand side becomes e to the power of log x, but e to the power of log, because their inverses cancel, and I just get x equals e to the power of y. So what I'll do here is, instead of finding dy dx, I'll find dx dy. Oh, differentiate e to the power of y with respect to y, it's e to the power of y. Well, that's dx to y, not what I wanted. I wanted dy dx. There it is, 1 over e to the power of y. Now that is the answer. It's just in terms of y rather than x. We would normally put it in terms of x, because everything's in, we say with respect to x. How do I do that? Well, that's okay, because look at the second line. I've got a little formula here that says x is e to the y. So the answer is 1 on x. That is, of course, not how we actually will end up differentiating logs, but that's how we could do it now without knowing how we differentiate logs. Okay, so there's a stack of questions there from exercise 6b, 6c and 6k to get ourselves back into the groove.